welcome back after lunch, everybody. Our next speaker is Luis Felipe Vargas. He's a PhD candidate at the CWI in Amsterdam, working under the supervision of Monique Laurent. And you can see his title already. So, Luis, if you're ready, please go ahead.
Yeah, thank you, Leclerc. Thank you, Etienne, sorry, for the introduction. Yeah, so the name of the title of my talk is Sum of Squares Approximation for the Copositive Cone and Approximations to the Stable Set Problem. And this is a joint work with Monique Laurent at CWI in Amsterdam. Okay, so let me start with the definition and motivation of the Copositive Cone. So a Copositive Cone is the set of symmetric matrices such that the form X transpose MX is non-negative for non-negative vectors. Here, non-negative vectors means entry-wise non-negative. And the Copositive cone or optimizing over the Copositive cone is important, as hard problems can be encoded as optimization over the Copositive cone. For instance, portfolio optimization, and motivated by this result by Buehrer in 2009, that every non-convex quadratic program involving continuous and binary variables can be modeled as a linear program over the Copositive cone. And then in particular, the stable set problem can be encoded as a linear program over the Copositive cone. And then optimizing over the Copositive cone is hard, as the stable set problem is a certifier for that claim. And even deciding whether a matrix is copositive is a hard problem. So in this talk, so today we're going to talk about three things in particular. So first of all, I will define some sum of squares approximation for the Copositive cone. Several, like maybe 4 or 5. And then we are going to apply the results in two settings. First, to study the exact approximations for the Copositive cone, which is related to non-negativity certificates via sum of squares of polynomials, and then an application to the stable set problem. Okay, so let me start with the first approximation, which is not a sum of squares approximation, but maybe it's useful to start. So that's the definition of the Copositive cone, as we already defined. So the set of symmetric matrices such that X transpose MX is non-negative for non-negative vectors. And then there are two subsets of the Copositive cone that are clear. Problems with my mouse. Is the set of positive semi-definite matrices. Of course, if a matrix is positive semi-definite, then it's copositive, just by the definition, because the definition of a matrix to be PSD is without the restriction of non-negative vectors, but for any vector in Rn. So of course, a positive semi-definite matrix is copositive. Another class of matrices, or another subset of matrices which is copositive, is the non-negative matrices, because of course the form X transpose NX, in that case, everything is non-negative, as all entries from N are non-negative, and from X also. And then the cone, we can define the cone SPN as the cone consisting of sum of positive semi-definite matrices and non-negative matrices is a subset of the Copositive cone. And optimizing over the cone SPN is a semi-definite program, or it's a semi-definite restriction constraint, and then it's easy, or it's easy to approximate, or can be done in polynomial time. Maybe it's the best way to say. And indeed, the cone SPN is equal to the Copositive cone up to n4. So for n less than or equal 4, we have that the Copositive cone is precisely the set of matrices which can be written as a non-negative matrix plus a positive semi-definite matrix. But this is not equal as expected already for the case n equal 5. As we can show, as we can see with the Horn matrix, is an example of a copositive matrix of size 5, which cannot be written as a positive semi-definite plus non-negative. And the Horn matrix is going to be crucial in our, or it's going to be important in the talk. So yeah. So it's an example of a copositive matrix, which is not in SPN. Okay, so now I'll define the first approximation based on sum of squares of polynomial, and was given by Parrillo in 2000. And then, okay, so we have the definition of the copositive cone, and then we are going to write a reformulation for the copositive cone by encoding the non-negativity of the variable into the variable. Yeah, so if we put this vector x to the square, which x square is each entry to the square, then of course we are forcing that each entry is non-negative, and of course these definitions are equivalent. But then we're going to use the second one, because the second one, what it's saying is that the copositive cone is the set of symmetric matrices such that this associated polynomial is non-negative. And then what Parrillo proposed was to use sum of squares of polynomials to approximate the copositive cone using this second setting. Okay, so yeah, so the polynomial P is a sum of squares of polynomials, or SOS, or sometimes we are going to refer to sigma as this set, if P can be written as a sum of squares of other polynomials. And then the first approximation Parrillo proposed is the approximation Kn0, which is the set of symmetric matrices such that this associated polynomial is a sum of squares. So not negative, but sum of squares. And indeed, he proved that it's equal to the cone SPN. So positive semi-definite plus non-negative. And he defined the cone KNR, but the set of matrices, symmetric matrices M, such that this polynomial is a sum of squares. So the first part is, is the associated polynomial, the x squared transpose M x squared. Sorry, are you seeing my mouse?
Yes, we can see it.
Yes.
Yeah, okay.
Yes, we see.
Okay, perfect. Okay, so this is the associated polynomial multiplied by a factor, so the sum of the squares of the variable to the power r. So of course, the cones K and R are contained in the copositive cone, because if a matrix is in K and R, then it implies that this polynomial is a sum of squares, which implies that it's non-negative. And since the first factor is non-negative, the second factor is also non-negative, which is the definition so it implies that it's copositive. And it's a hierarchy of approximations. So it's a cone that satisfy this property. KNR is contained in KNR plus 1 and can be easily seen because, yeah, if M is in KNR, then this polynomial is a sum of squares. And then when we multiply by the sum of the squares of the variables, the sum of squares times sum of squares is also sum of squares. So, of course, belongs to KNR plus 1. And these cones help because, as we saw in the previous slide, the Horn matrix is not in the cone Kn0, which coincides with the SPN, but it's already in K51. So this cones, so it's a certifier that Kn0 Kn1 is bigger than Kn0. And this is based in the following lemma, that the interior of the copositive cone is contained in the union of the KNRs. And this follows from the Resonant Theorem. It says that if P is a homogeneous polynomial such that is strictly positive on Rn except on 0, then there exists a power of the sum of the squares of the variable such that is the sum of the squares. So of course, if a polynomial is strictly is in the interior of the copositive cone, then belongs to some Parrillo cone. Okay. Now I will define other cones that are based on Lasserre type certificates, or based on polynomial based on the Lasserre hierarchy of Lasserre sum of squares hierarchy for polynomial optimization. And then for this, we're going again to rewrite the definition of the copositive con. So the first one is the original formulation. And the second one, so we can verify easily that we can put the constraint, not x greater than or equal 0 for non-negative vectors, but adding the constraint that the sum is equal to 1. We can normalize the sum of the entries. And then we're going to use this second formulation for the following observation. So if we can write the polynomial x transpose mx, if we can decompose it in this way, then the matrix is copositive. Yes, because if we take x in the simplex, then the last term is going to be 0, and the first two are going to be non-negative. So it's non-negative on the simplex, which means that it's copositive. And then based on that observation, that is what is used in the sum of squares hierarchy, Laser hierarchy for polynomial optimization, it motivates to define the following cons. So we're going to call the Laser con, the Laser simplex con at level R is when such a certificate exists and imposing the constraint in the degree of the squares up to degree R. And we can define the Laser preordering con at level R, and now allowing not just xi times a sum of squares, but a product of the variables, product of the xi. So we can consider here x to the beta when x to the beta is any monomial up to degree R and with a sum of squares. So by the observation, then it's easy to observe that these inclusions hold. These are subsets of the copositive cone, and the interior of the copositive cone is contained in the union of the Laser simplex cones. This is just another way to state the Putina's theorem. In the particular case of the simplex, which is Archimedean, so everything is okay. Okay, so we have these two cons, and now we are going to define another formulation, another cons for approximating the copositive cone. Okay, so now we write the copositive cone with encoding the non-negativity into the variables, so with the x squared, and then again we can consider we can restrict ourselves just to the vectors for which the sum of the squares of the variables is equal to 1, so the unit sphere. So we can change the formulation for this, and then we have again the observation. So if we can write this polynomial as a sum of squares in the ideal of the unit sphere, and then M is copositive, and then it motivates to define the cone, the Laser cone based on the sphere, or the Laser sphere cone, which is also contained in the copositive cone, and we can prove the following lemma, that is the Laser simplex based cone is contained in the Laser simplex preordering cone, as we observed in the previous slide, and is contained in the Laser cone based on the sphere at level 2R. So here we're going to prove that the first cone is contained in the last one, but the proof that the second is contained in the third is the same. So just for simplicity, let's prove that the first one is contained in the last one. So if we take M in the first cone, it implies that we can write X transpose MX as such a certificate exists with the constraint of the degree of the squares. So we have that certificate, and then we are going to evaluate in X squared. So each variable to the square, and then what we obtain is the following. And then, of course, sigma 0 of x is a sum of squares. Then when evaluating at the square, it's also a sum of squares. And then in this second part, what's happening is that sigma I evaluated at x squared is a sum of squares, but now it's times a square. So this is a sum of a square, So the first two parts together are going to be a sum of squares. So it's a sum of squares in the unit sphere, because in the simplex, when evaluating the square now is the unit sphere, but now the degree is going to be 2r. So it's an easy proof. If we start with something in the Laser cone based on the preordering, is going to be the same. So this is easy. Okay, so maybe I didn't mention, but maybe you already know that optimizing over these cones is based on sum of squares of polynomials, so can be done by a semi-definite program. Okay, so in the next slide, now we are going to relate all cones hierarchies we have defined by the following theorem. So that the Laser hierarchy, the Laser cones based on the simplex is contained in the rest, and the rest are actually equal up to some degree correction. And then to prove that, okay, so first of all, the first these inclusions we have by the previous slide, and this second equality here is an r. So kn r minus 2 is equal to the Laser cone based on the sphere at level 2r, and this was proved by de Klerk, Monique, and Parrillo in 2002. So it remains to prove that the cone kn r minus 2 is contained in the Laser cone based on the preordering at level r. Okay, so let's write the definition. So the definition of M is in the cone kn r minus 2 means that this polynomial is a sum of squares. Now we're going to use a theorem by Peña, Vera, and Zuluaga that, okay, so the theorem says the following. So if you have a homogeneous polynomial of degree d, such that when you evaluate in x squared is a sum of squares, then we have information about q. Yeah, so if the polynomial is evaluated at each variable to the square, then we know information about when forgetting the squares or when we don't have the squares. And this is precisely the case. Now we have this polynomial is a sum of squares, and each variable is to the square in this polynomial. And then by this theorem, then we have that now the theorem without the squares has this form, which is very similar to a preordering form. And now if we write the sum of xi's as sum of xi's minus 1 plus 1, then this power has one term which is going to be 1 to the r minus 2, which is 1 times x transpose mx is x transpose mx, and the other terms are going to be divisible by the sum of xi minus 1. So it's a polynomial times the sum of xi minus 1, which means precisely that x transpose mx is in the cone of the preordering, because it's this form of the preordering times, if we put this minus to the other side, plus something in the ideal of the simplex. Okay, so it concludes the proof, which relies basically in the theorem by Peña, Vera, and Zuluaga. Okay, so Peña, Vera, and Zuluaga define another cone QNR, which is based on the following observation. So they proved by the theorem they showed that that M is in the cone KNR if and only if this polynomial, now without the squares, has this form. So it's like the sum of x to the beta times a sum of squares, x to the, so it's considering any monomial up to degree r plus 2. Up to degree r plus 2 with a sum of squares, the multiplier, which is a sum of squares. So what they consider is the cone QNR, which is when such a decomposition exists, but just considering the monomials of degree r or r plus 2. And this in practice is much better, because now we have just to consider the sum of squares with degree 0 or 2. And yeah, this is, of course, is easier to implement that than the cone KNR. So okay, so and then by the trick of writing the sum of xi minus 1 plus 1, then we obtain that M is in QNR if x transpose mx can be written in this way, just by considering the monomials of degree r and r plus 2, and then the squares of degree 0 and 2. So also this expression looks very similar to a laser type representation. And then maybe to summarize in the next slide, so then we can see the following claim. So all hierarchies that we have defined are variation of the laser simplex base hierarchy. This is because of the following. So M is in the con KNR if and only if M is in the laser preordering bound at level R+2, as we showed in the main theorem. And it means that X transpose MX has such a decomposition, in the preordering based, so in the preordering based on the simplex, yes. And then, okay, so then the yellow is the KNR. So KNR involves all terms. So M belongs to KNR if such a representation exists using all terms, or if you use all terms. And the laser hierarchy is using just the first sum of squares and the sum of squares with xi. And the QNR cone is using the other part of the squares. So like the monomials with x to the beta, when beta is of size r, and okay, beta or alpha is of size r+2. Yeah, so this is what I mean with these are variations of the laser simplex base hierarchy. And then from this is clear that Q and R is containing K and R, and that the laser is contained, the laser simplex based cone is containing K and R. But we don't know what happened with Q and R and the laser. Maybe are not comparable simply. Okay, so maybe it's a good moment if you have questions. Not, I can continue for the first application. No questions. Okay, so now I'm going to talk about exactness of sum of squares approximation for the copositive cone, in particular of the cone K and R. So we are interested in when is the case that the cones K and R approximate exactly the copositive cone. So as we mentioned before, the cone Kn0 is equal to the copositive cone when n is less than or equal 4. And Parrillo asked, is Kn1 equal to the copositive cone until up to some n? And the answer is no, and is given by the theorem by Dickinson and co-authors that says that KNR is not equal to the copositive cone for any n at least 5 and R and for any R. And then we have the following question: is it true that the copositive cone then is equal to the union of the K and R for some n? Because we know that for n less than or equal 4 is true, but we don't know for the rest. And then we prove that this is not true for n at least 6, and is by the following theorem. So if we have a copositive matrix which is not in the first Parrillo approximation, so it's not in Kn0 or in the con SPN, positive semi-definite plus non-negative, then the matrix obtained by adding one zero-row column is again copositive, of course, but does not belong to any of the Parrillo cones. Yeah, so this is one of the one problem from the Parrillo approximation, that is when we add zero-row columns, it's outside not from the cone from each of the K and R. It's like it's not in every. So if it's in K1, for instance, and not in K0, then when adding one zero-row column, is not in any of the cones. So for instance, if you start with the Horn matrix plus a zero-row column is not in any. It does not belong to the union of the K and Rs. Okay, so that's the proof. Maybe I'm going to skip the proof. But then the question, the remaining question is the copositive cone of size 5 equal to a union of the K5R? And then we okay, so let's talk about the the copositive cone of size 5. Then let me say what a diagonal scaling is. So a diagonal scaling of a matrix M is a matrix of the form DMD when D is a diagonal matrix. And then some properties is that the cone K and R are not closed under diagonal scalings. And the diagonal scalings of the Horn matrix of H are extreme rays or define extreme rays of the copositive cone. Okay, so and then we have the following theorem. So if H is the Horn matrix, then we have that the union of the K5R is equal to the copositive cone of size 5. So we have exactness if and only if the diagonal scalings of the Horn matrix belongs to the union of the cones K5R. So in other words, it's sufficient to look at the diagonal scalings of the Horn matrix. The sketch of the proof might be not the sketch, but the idea is that the extreme rays of the copositive cone of size 5 were characterized by Hildebrand in 2012. And then using this characterization, we can prove that any extreme matrix or extreme ray, which is not of the form diagonal scaling of the Horn matrix, for this matrix, we have that belongs to the union of the Laser simplex-based cone. So it's even stronger the result. But what we also can prove is that the Horn matrix does not belong to any of the Laser-based cones. So it's still open if the union of the K5R is equal to the copositive cone of size 5. But yeah, so we have this theorem that it's sufficient to look at the Horn matrix and its diagonal scalings. Okay, so now we're going to talk about the application to the stable set problem, which is the main motivation for my in my project. So I'm looking at these copositive approximations, these sum of squares approximations motivated by the problem I need to show. Okay, so the stability number of a graph. So given a graph, a subset of vertices is stable if S contains no edge, and the stability number of a graph is the maximum size of a stable set. So for instance, in the Peterson graph, the blue set is stable of size 3, and the red set is stable of size 4, and the stability number is 4, and yeah, it's easy to check. And then, okay, so a starting point for defining approximation hierarchies for the stability number is the Motzkin's transformulation, which says that 1 over alpha of G is the optimal value of this minimization problem over the standard simplex. So a quadratic form over the standard simplex. And then, for example, if S is a stable, then when we evaluate that the indicator and the scaled indicator vector of S, then we obtain that the value is 1 over the size of S. So it means that if we take a maximum stable set or one stable set of size alpha, then the optimal value is going to be 1 over alpha. So any maximum stable set gives an optimal solution for the problem, but they are not the only ones, as we're going to see later. Okay, so Declerc and Pasechnik in 2002 proposed a reformulation for the stability number as a linear program over the copositive cone. So alpha of G is the minimum T such that the matrix T times AG plus I minus J is copositive. Here, AG is the adjacency matrix of the graph, I the identity matrix, and J is the all ones matrix, which also can be seen as E times E transpose. Okay, so and the proof is easy, but it's very nice to see the problem as a optimization over the copositive cone. So for this, let's take a feasible point for the problem, and then okay, so it means that this matrix is copositive, and then by the definition, X transpose that matrix is non-negative for vectors in the standard simplex. And then we use the fact that X transpose Jx is equal to 1 because E transpose X, so the sum of the variables is equal to 1. And then, okay, so I'm not going to show in detail, but this is to observe that alpha is indeed the optimal value. Okay, so now, based on that formulation, on the copositive formulation for the stability number, alpha is equal to the minimum t such that that matrix is copositive. The Clerk and Pasechnik proposed the hierarchy theta r of G based on the Parrillo approximation. So recall the Parrillo cons for approximating the copositive cone, which is the set of symmetric matrices such that this associated polynomial times a power of the sum of the squares of the variables to the R is a sum of the squares of polynomials. And then the Clerk and Pasechnik proposed the hierarchy based optimizing over the Parrillo cons, which amounts to a semi-definite program for each level. And yeah, so there are some results about this hierarchy. Is that, yeah, so it's indeed a hierarchy of approximation. Is improving and improving as R increases. That's because the cons K and R is containing K and R plus 1 for any R. And also converge asymptotically to alpha as R goes to infinity because yeah, the interior of the copositive cone is contained in the union of the K and R. And also theta 0 of G, so just considering sum of squares without multiplying this. So the first level of the hierarchy is equal to theta prime of G when theta prime is the lowest theta number by adding one non-negativity constraint. Also, the Clerk and Pasechnik proved that the bound theta R is between alpha and alpha plus 1 for R greater than or equal alpha square. So the hierarchy after alpha square can find alpha because you can round to, it's between alpha and alpha plus 1, and then rounding, you find alpha. And then one question that we have is, when do we have, so when is the case where theta 0 of G is equal to alpha of G? It's more about the exactness of the approximation at the level 0. This is also one, yeah, interesting question. Okay, so then the Clerk and Pasechnik proposed one hierarchy, one conjecture about the hierarchy. So let me define the theta rank of G is the minimum R such that theta R of G is equal to alpha of G. So it's the minimum number of steps that the hierarchy needs to find alpha exactly. In other words, this is saying is the minimum R such that this associated matrix Mg, which is alpha times Ag plus I minus J, belongs to the cone K and R. So it's the minimum R for which this matrix belongs to K. And then the first conjecture by the Clerk and Pasechnik is that this theta rank is less than or equal alpha minus 1. So that the theta alpha minus 1 of G is equal to alpha. So in other words, is that this matrix, Mg, belongs to the cone K and alpha minus 1. But even the weaker condition, the weaker conjecture of finite convergence is open. So that asks whether the theta rank is finite. That is, if the matrix Mg belongs to K and R for some R in N. So this is our interest for considering when the copositive cone is equal to the union of the K and R, because we don't even know whether this weaker conjecture is true up to some R. Okay, so some known results is that the conjecture 1 holds for perfect graphs with R equals 0, and for odd cycles with R equal 1, and their complements also. Also, conjecture 1 holds for graphs with a stability number at most 8. It's proved in 2007. And in this case, it's even true that this matrix Mg belongs to the cons Q and alpha minus 1 that are contained in in the cons k and alpha minus 1. And then we can ask like whether this conjecture could be true not for the cons k and r, but for the cons q and r. And then, yeah, so we observe that if this is the case, that the conjecture is true even for the cons q and r, then the conjecture 1 should be tight. It means we found some graphs for which we can prove that the graph is not in the con q and alpha minus 2. So if the conjecture is true, it should be precisely in alpha minus 1, which is okay. And yeah, one of the main results from this talk is that we prove conjecture 2, so finite convergence for the class of acritical graphs. I'm going to define what a critical graph is. Okay, so now the role of critical edges. So first the definition. So an edge of a graph is critical if when deleting the edge, the stability number increases. And we said that the graph is critical if all edges are critical, and acritical if no edge is critical. So for example, the cycle of size 5 is critical, while of size so even cycles are acritical. So for instance, this 5 cycle, the stability number is 2, and if we delete, for example, this edge, then the stability number is 3, and by symmetry, we can observe easily that all edges are critical. And the Peterson graph, for instance, is acritical. And then the observation for considering critical edges is the following. So if you delete one critical edge, then the theta rank can only increase. This is because, okay, so if a graph belongs to the con k and, so if when deleting the edge, the graph belongs to k and r, meaning that this polynomial is a sum of squares, then the graph with the edge is going to be also a sum of squares, because we are adding just non-negative terms. So it's actually an easy observation, but then it's sufficient to prove conjectures 1 and 2 for critical graphs, because we can start with the arbitrary graph and then start deleting critical edges, non-critical edges, until we obtain a critical graph, and then using this observation, then it's sufficient to prove conjectures 1 and 2 for critical graphs. Okay, and what we can do is characterize the graphs for which the theta rank is 0 in the case when G is critical. So if G is critical, the theta rank is 0, or the first level of approximation is exact, if and only if G is the disjoint of clicks. So it's actually an easy class. Yeah, maybe we can do this together. Okay, so if we have a graph that is in the first level of approximation, k and 0, if mg is in k and 0, it means that mg can be written as positive semi-definite plus non-negative, with the diagonal 0 in the non-negative, because if it's not 0, we can put these values to the diagonal of the positive semi-definite matrix, and it's okay. And then what we are going to do is to evaluate. So let's consider. So if we have an stable set of size alpha, then let's consider the indicator vector of this set, and then we multiply x transpose mgx. So is 0. This is easy to observe from the definition of mg, and can be decomposed in these two, in x transpose px plus x transpose nx, which are both non-negative. So since this is 0, both of them should be 0. In particular, x transpose px is 0, and p is a non-negative, it's a positive semi-definite matrix, so it implies that x is in the kernel of p. So okay, so the idea is that if S is a stable set of size alpha, then the indicator vector of the stable set is in the kernel of the matrix P, which is in the composition here always. This is the property. And now if we take ij a critical edge, so being critical, what means is that if you delete this edge, there is a critical, there is an unstable set of size alpha minus 1 containing both nodes. So it implies that there exists a subset such that with I is of size alpha and with J is also of size alpha. Yes, that's the definition of critical. And then using the previous property, it follows that the indicator vector of I minus the indicator vector of J is in the kernel of P. This is by doing, the indicator by subtracting. And then it implies that the columns, the ith column and the jth column from P are identical. And then, so we can see that if C is a connected component, the graph, then we can show that that is a clique. Maybe I'm going to skip this part. And then what we show is that deciding whether a graph has rank 0 can be reduced in polynomial time to the same questions for a critical graph. So it means that studying the conjectures is difficult for critical graphs, while studying whether a graph has rank 0 is difficult for a critical graph. Okay, and now our main theorem is that if G is a critical, then we have finite convergence. But the result is even stronger. We prove that if G is a critical, then the matrix Mg belongs to the Lasserre type cons based on the simplex, which are contained in K and R. So, and thus, it implies that Mg is contained in K and R for some R, which means that theta R of G is equal to alpha of G for some R. Okay, so the sketch of the proof is thinking back in the Motzkin-Strauss formulation, and now with the following observation that finite convergence of the Lasserre, of the sum of squares Lasserre hierarchy for the Motzkin-Strauss formulation is equivalent to prove that Mg belongs to some of the Lasserre cons we defined at the beginning of the talk. And then some important points is that the minimizers for the Motzkin-Strauss formulations are the ones coming from alpha stable sets where S is a maximum stable set. So this is something that happens just in the case of a critical graphs, and the classical optimality conditions hold at every global minimizer. And then using a real algebraic result from Marshall and Nee, we obtain finite convergence of the Lasserre hierarchy, and then we can conclude our result. Maybe some comments is that the classical optimality conditions can hold, if they hold, that it implies that we have finally many global minimizers. And in the case of the Motzkin-Strauss formulation, we have finally many global minimizers if and only if the graph is acritical. So this idea can be only used in the case of acritical graphs. And the other important thing is that finally many minimizers does not imply in general finite convergence of the for a standard quadratic program. So it's not it's just the case of Motzkin-Strauss formulation. Okay, and then now we have a theorem of the minimizers of the Motzkin-Strauss formulation. Actually, we have a nice characterization is that if we have a feasible point for the Motzkin-Strauss formulation, so a point in the standard simplex, and then we take the connected, so induced subgraph of the support. So we take the support of the solution and we take the induced subgraph, and we consider then the connected components of this graph. Then X is an optimal solution if and only if there are alpha connected components. Each of them are cliques, and the sum over this connected component is equal to 1 over alpha. And in that case, all edges of this induced subgraph are critical. So for example, in the case of C5, we know that the stability number is 2. So the connected components of the support should be the disjoining of 2 cliques. So it should be of this form, one edge and one node. And in each connected component, the sum should be 1/2. So, and then we can actually characterize the minimizers for this case. And then the important observation, one important observation, is that the only edges in the support of an optimal solution are critical. Yeah, so it gives now one complexity result that we ask, what is the complexity of deciding whether a polynomial optimization problem has finally many global minimizers? We're interested in having finally many minimizers in order to apply the results by Nia and Marshall. Can only hold in that case. Then, okay, so we have this question. So the first case is when it's a linear program, and deciding whether a linear program has finally many global minimizer is in P, is easy to solve. And then what we propose now is that based on the previous theorem, that we know that in an optimal solution, the only edges are in critical edges. So the only edges are critical. Then we are going to take the Motzkin-Strauss formulation, and we are going to perturb all entries except the entry ij, or the entry given by the edge e. Okay, so it's easy to observe that the optimal value is again 1/alpha, because there are minimizers supported in a stable set. So if we perturb something which is not in the diagonal, then the optimal value is going to be the same. Yeah, of course, if we perturb with a positive value. Okay, and then this problem has finally many global minimizers if and only if the edge E is not critical. And then we can also show that deciding whether an edge is critical is in P. If this is in P, it implies that the stable set problem is in P, because we can start, if we have a polynomial time algorithm for deciding if an edge is critical, then we start with a graph and we take one edge, and then we ask, is critical or not? If it's not critical, then we delete the edge, and we know that the new graph has the same stability number. And if it's critical, we delete the edge, and we know that the stability number now increases by 1. And then doing this process until the end, we know how the stability number changed, and then when we end up with the empty graph, which stability number is n, we can recover the stability number of the original graph. And then we have the following theorem that unless P is equal to NP, there is no polynomial time algorithm for deciding whether a polynomial optimization problem, even a quadratic one over the simplex, has finally many global minimizers. Okay. Yeah, still I have time. Okay, so and then I'm going to finish with some comments about the isolated nodes, which is one property that is difficult to analyze in that problem. Is the following. So consider G plus I0 is the graph obtained by adding one isolated node to G. Okay. So the question is, what is the relation between the theta rank of G and the theta rank of a graph plus adding one isolated node? Okay, so recall this is MG, and then this is motivated by the following lemma. So if the theta rank does not increase when adding one isolated node, then the conjecture 1 is true. So the stronger one is true. So in other words, what it's saying is that, yeah, so if MG is in KR, and then the MG plus one node is in KR, then conjecture 1 holds. But the bad news is that this is not true. And actually, we can characterize for some graphs how many nodes we can add so the rank remains equal. So if G is a critical graph with rank 1, then yeah, we can compute the exact number of nodes we can add so the rank is the same. And then, for instance, if we take the cycle of size 5 and we add 8 isolated nodes, so the rank is the rank of this 5 cycle is 1, and if we start adding isolated nodes, the rank is 1, 1, 1, 1, 1, until we add 8 isolated nodes, and when we add 9, the rank is 2. So it's a behavior, a strange behavior that we cannot understand so far. So adding isolated nodes can increase the rank. So this idea from this lemma for showing conjecture 1 does not work. And then, but what we have is that conjecture 2 holds if and only if adding isolated nodes remains the theta rank finite. Okay, so let me finish with some summary and conclusion. So what we do today was to define several cons for approximating the copositive con based on sum of squares of polynomials, and we link them, and we saw all of them as a special case of Lasserre type cons. In the second part of the talk, we discussed about the exactness of the approximation K and R for the copositive con. And yeah, we motivate the question if this is it true that the copositive con of size 5 is equal to the union of the con K5R is still open, but it suffices to look at the diagonal scalings of the Horn matrix. And in the last part of the talk, we revisit the hierarchy theta R by de Clercq and Pazesnik for approximating alpha of G. And then some important facts is that it suffices to show the conjecture for critical graphs. We could show finite convergence by conjecture for acritical graphs at the other side, and we partially characterized the graphs for which theta 0 of G is equal to alpha G. So for the first level approximation, it's exact. Thanks for your attention. Yeah, so there are some references.
So thank you very much, Luis. Are there any questions? I don't see in the chat, but please just unmute yourself and ask if you have a question. So just to set the tone, Luis, I have a question. I may have asked this before, but I don't remember. So the decision problem to decide that a given graph is critical. I guess this is NP complete.
Yes. So deciding if one edge is critical is hard. Is NP hard. But I think deciding if the whole graph is critical, I think it's another class of complexity. So it's hard, but I'm not sure that I think it's not NP complete. It's something like DP or something like that. I saw in one book from law. I meant to share with you the exact complexity class, but I think it's another one.
Okay, great. So I am looking for more questions. So no, it is quite quiet. So if there is nothing else, let us thank Luis again for the very interesting talk. So it was very nice. Thank you very much. And then we will resume at 3:30 with the last talk for this afternoon. So see you in a little bit more than half an hour.